Right, our next speakers are going to be Lin Yan and Ori Fox that are going to talk about also Roman and Rise.
How do I advance things?
Oh,
It's not dying.
it died.
Okay. So now you have heard from Ben and Jacob how rapid find transient candidates from a single frame images. Ori and I will tag team and talk to you about the RISE project. This is one of the approved Roman wide field science programs selected in 2025. And the basic idea for this project is to search for high redshift transients by using image stacking and subtraction method. High redshift transients are already being discovered in deep GWST images. This figures from Ori's recent paper summarizes their results, showing in the more than 120 supernovae they discovered in these multi-epoch GWST images in JADES and Cosmos fields. And the figure shows that these supernovae find with a magnitude spanning over from 24 to 30 and a half over the entire redshift range between 0.5 to 5. And what's amazing about this figure is that's showing this shaded region here, that this is shaded region is exactly the region that where Roman single frame as well as RISE stacked images will reach the depth. Another spectacular event I want to highlight here is this object called SN 2025 WNY. This is a superluminous at redshift 2 and gravitationally lensed by a foreground galaxy. And this event was first discovered by ZTF last October as a bright transient with a magnitude of 19.5. Once the reference frame got subtracted and revealed that this transient, this image A, actually has 3 additional lensed images. And the Keck spectra taken of the image A confirmed the redshift at 2, and also the spectral type is shown to match with the superluminous type 1. So these cases essentially highlights the science drive for RISE project. I think the basic idea is really that we are trying to explore this new frontier at the early universe where we really don't know that much about the dynamic universe at these high redshift. And we want to answer a lot of these questions. For example, the massive stars at high redshift tend to have low metallicities. How that impacts the supernova population is really unknown. So we really need to first detect these transit events and build a light curve in order to answer all these questions. So how deep can RISE stacking method reach? So these 2 figures basically summarizes the range of the depth that we can reach. For the white high latitude time domain survey, and the single frame can already reach to 25 magnitude in J band. And once you stack 6 frames, it's already 1 magnitude deeper. So you already reach about 26. And then if you stack 18 frames, that's another half magnitude deeper. In the deep high galactic latitude time domain survey, it's whole magnitude deeper. So the takeaway is that the rise stacking allows you to reach in the range of 26 to 28 over a various area with a time span of 5 years. So with such a condition, what types of high Z transient would you expect that rise would detect? The first two top candidates are these intrinsically luminous and slow evolving events. One is a superluminous event, and then the one type is tidal disruption. And both of these type of sources we have, the ZTF have in the past 7 years have collected large number of large samples of both types. And these light curves and as well as spectral sequence can serve as templates for the Roman results. And we calculated the expected J-band light curve for superluminous supernova events based on the theoretical model. There was two types. One is electron-positron instability supernovae, and the second one is the superluminous supernovae powered by magnetar model. As you see that the point here, I want to emphasize that the rise stacking not only allows you to detect these sources, but also allow you to not fully, but sample multiple data epochs, which allow you to have a trace of the shape of these light curves. So this is important for the characterization. A similar kind of calculation was done for tidal disruption event by Robert Stein and Yuhan Yao. And here we see that the expected number of TDE at high redshift is actually quite high. It's very substantial. So this is very exciting. There's a third category, which is really exciting, is for these normal core collapse supernovae. Normal core collapse supernovae is intrinsically lower luminosity than superluminous supernovae. So we expect that the detection redshift range will be somewhere between 1 to 3. And so the calculated number, the sample of these sources is quite large. What's most exciting about it is that when you use these large sample, allows you to measure the volumetric rates as well as the luminosity functions as a function of redshift. And this number allows you to constrain the stellar IMF directly from this plot. Here, these open square blue points are previous published results. They're very highly uncertain with very large error bars. And anticipated Roman results are the purple square. So we hope that these results will constrain these theoretical models from these dashed lines much better, which essentially constrains the stellar IMF. Before I hand this the second part of the talk to Ori, I want to talk a little bit about what we have done to the RISE pipeline. So here's some initial results. Using the Open Universe simulation data, we have run the OAGEN to produce the stacked images. And here basically shows that this is a single frame, and once you stack 10 frames, very faint sources start popping up. And then expected signal to noise ratio as a function of this number of frames that you stack, it's increasing as expected. And this is good to know that the OAGEN software works well. And what's more important is that we run these stacked images through the image subtraction pipeline. And here, this is the deep reference image without transient. And this is the stacked image with the transient in the center. And it's nicely recovered. And you also notice we do have some, they're not perfectly subtracted out. This is because we still need to work on the PSF matching, and hopefully the improvement will be coming. I'm going to stop here, and Ori will take over and then talk about what's a deliverable from RISE and also the general Roman survey plans.
Okay, for those of you who don't know me, my name is Ori Fox, and my official title at Space Telescope Science Institute is the SOC, the Science Operations Center Deputy Project Scientist for Roman. And I'm going to do something very dangerous today. I'm going to speak to you in two capacities, one as a scientist and another in official capacity as the Deputy Project Scientist, because I have to justify my travel budget. And I only have 7 minutes to do it. So, and I already wasted 30 seconds. How do I, there we are. Okay, so to pick up where Lynn left off, detection is only the first part of the battle. Then we got to get that information out to the community, and we need to make it valuable to the community. And so there are a number of different deliverables that RISE intends to make, and a couple of improvements that still have to be implemented in order to really optimize the science. So this is all published. If you're not aware, all the different PITs and WFS teams have put out a list of deliverables that they plan to make to the community. It's on Goddard's website. We are going to produce an image coad, subtraction, and faint alert pipeline with the rapid stream. We will have a machine learning real bogus classifier, but then we're going to also include some post-alert characterization and prioritization for the community. Some of that value-added analysis is going to include force photometry light curves, where we can actually go back with the stack detections and perform force photometry for single epoch light curves, which will enable much more robust light curve fitting. We'll talk about that in just a second. We're also going to provide some initial light curve fits using existing models and fitting algorithms. We also want to provide some initial photometric redshifts using the Roman data alone, using a range of different photo Z fitters, which you'll hear about a little bit more later in this workshop. We also want to provide some constraints from colors and some initial machine learning prioritizations. But there's still a lot of limitations in this value-added analysis that we are going to provide through RISE. And I just want to highlight more work that we still need to really think about on the team in the future. This is a plot from Anya Nugent, she'll be speaking tomorrow, that shows you the scatter when you perform photo-Zs with just the Roman photometry compared to when you combine it with Rubin photometry. Combining it is not trivial, and so that's an extra layer of work, but you can see how much better adding that Rubin data does for the photometric redshifts, especially at around redshift of 1. You don't want to be thinking that you have a redshift 1, 1.5 to supernova when it's really 0.5. This is an example of some anticipated light curve fits that you might get from a typical type 2 supernova at 2.5. This sounds crazy, but we're expecting, as you saw from Lynn's plot, we're expecting thousands of core collapse supernovae at redshifts 1 to 3. we're going to have to characterize these. So these are some example light curves that you might anticipate if you went back and did force photometry at the position of these stacked detections. You're going to have, you're at 27th magnitude, really low signal to noise, a lot of non-detections. And right now, this is the state-of-the-art fits from Stardust 2, which works off the supernova Cosmos. I don't actually do the fitting myself. This is from the team, Krista DeCursi in particular, that just shows you how difficult it is for current fitters to actually work with the data sets that we're going to have. So there's going to be a lot of modifications made that we think are going to lead to potentially something like Stardust 3. And then we want to integrate all of these different inputs to some sort of machine learning classifier. And we have a lot of ideas that I'm going to throw up on the screen here. But the truth is, nobody on our team right now actually does machine learning. And so we're learning. We're learning in real time. This is why I'm asking for help. This is why I'm at the conference. I'm going to be here for the hacking. We're going around. We're doing a lot of learning. We are going to get there. I'm fully confident in our team, but we have a lot of work to do over the next 1 to 2 years to actually make this happen. And I've talked to many of you about this already. So to conclude that part of the talk with my science hat on, I just want to say that high-Z supernovae really represent the next frontier in time domain astronomy. This field is completely open. There's still a lot to learn. We anticipate that it's not just an extension of low redshift time domain astronomy. It's really new physics, new types of stars, new environments, POP3, the whole shebang. So, this is the next frontier. And Roman is going to be able to do this unlike any other telescope in terms of combined depth and area. We didn't get into a lot of the science, but details. But the key thing is that JWST obviously can go deeper, but you need area because a lot of these things require large numbers or large areas or large volumes to actually do the science. And RISE is going to help get us there, but we can't do it alone. We do need spectroscopic follow-up in some cases. We need JWST, we need Rubin's optical light curves. So we're working with a lot of observatories to combine and make one large program. Okay, so in the last 3 minutes, I just want to switch over to my deputy project scientist hat on and say that even though RISE was one of the WFS programs chosen for Roman, it is not the only science you can do with all the community surveys. I just want to really highlight how much time domain science is out there. You've already had an introduction to the fact that there are these community defined surveys. They represent 75% of the mission. And they all have they all have science drivers, but they are not designed for any one science goal in mind. I want to make this very clear that the committees that define these surveys took in white papers from everyone and tried to optimize the science for the entire community. So if you think that there's already science that has been picked off by certain teams, that is not true. Nobody owns the science. And furthermore, there is not one science goal for any one of these surveys. I can't make that clear enough. I have a couple fun slides here that highlight just, in numbers, how many great things are going to happen. But I want it for each of the surveys. We have the high latitude wide area survey. And, wide area survey, you might only have one epoch, but I just want to make this point. The wide area survey covers over 3,000 historical supernovae from the past 50 years that are just ripe for the picking. So, I want to just say that even with one epoch, you can still do a lot of time domain science. And then, of course, we have the galactic plane survey. I'm running out of time. Galactic bulge time domain survey. A lot of great science hidden in here. There's ways to explore these surveys. We have a lot of training material online, a lot of documentation so that you can get a sense about whether you can do your science with these surveys. I encourage you to come back to this slide and check out all the tools that the SOC and the SSC have put together. I also want to say that you don't have to do this alone. The SOC and the SSC are producing data releases and data products that will enable you to do your science. You don't have to work at the image level. You can work at the catalog level. There's a lot of details provided. I encourage you to go to that QR link. But most importantly, I want to say get involved, because a lot of you might feel that the bar is really high. You don't have a place in Roman. Where do I even start? I just want to say we are reaching out to the entire community. There are many ways to get involved, but the easiest way is just to sign up for our social media, Nancy Roman side. We're on all the major platforms, and we give multiple alerts every week about training, workshops, presentations, meetings, webinars, you name it, and we welcome you to the community. So I will end there. Thank you.
All right. Thanks, Ori. And then I'm sorry, but we have zero time
That's
for
okay.
questions, so please save them for the discussion. Sorry.